Hi, my name is Brian. In this video, we'll be covering the Driven Pendulum Computing Project problem. We'll be covering how to modify your old code to work for this computing project, physical properties, initial conditions, changing from x to theta, storing relevant information, and calculating energy. So the first thing that you want to do is duplicate one of your old codes, preferably an old code that already has Newton's method inside of it. That's going to be the easiest thing to start from. You want to duplicate an old code. Don't just start erasing what you already have. That way you can always go back to a state that you know, and then you can also keep your old code if you need it at some point in the future. And of course you want to update your comments here as well. So let's just go ahead and look at the problem geometry really quick. So we have an inclined plane rotated up from the horizontal by an angle phi. So we have this P, and in our input physical problem data section, we always want to put data about the problem that doesn't depend on time. So for instance, we have this pendulum of length L. L is a constant that's not going to change with time, so we're going to want to put it in this section. And then we have this pendulum moving up and down this inclined plane, and we drive it with the forcing function where we define our x naught, and we also define our capital omega, that's the chosen amplitude and the chosen frequency. So we choose these, and they also do not depend on time. And of course we have our pendulum swinging about the roller at an angle theta, and that does depend on time. So we'll have to initialize our problem information. So we're going to have an initial theta, an initial omega, an initial angular acceleration as well. So in past CPs, we've dealt with initial conditions with three pieces of information, the x, y, and z information, but now we're dealing with angles. So we actually want to switch from x, y, and z to just an angle. So we switch all of our information or our vectors to scalars because we just need the rotation. We need the rotational velocity and we need the rotational acceleration. Now you're not going to need to actually change the variable names in your MATLAB project because that would be time consuming and very error prone. Just change how you think about them basically. And then also they're going to be changing from vectors to scalars. You only need to keep one piece of information. So just keep track of that idea. And as you're changing your code, make sure you understand that some of your code might act differently and you need to update that. So this next section is for planes and normal vectors. So you can go ahead and get rid of this since we're not going to be dealing with normal vectors for impact. Next, we have our numerical analysis parameters, and we're going to need these two parameters, but since we're going to be dealing with a nonlinear equation, we're also going to need other numerical parameters, and I'll talk about that in a minute when we get to Newton's method. So here, the one thing that you're going to want to remember is for the n items variable, for the history array, when you're initializing the history array, later, as you update the history array and the information that you want to store, update this value, otherwise it will not run the code. And here's just outputting to the command window. Here we initialize our t, out, I out, and then x old and v old, and those can all stay the same. And then we initialize our a old with our equation of motion, so that can just be from what you solved by hand already. And then the next thing we're going to do is we're going to start our time stepping algorithm, and here we're going to be, as usual, storing to our history array. And the first thing I want to focus on really quick is the change in the energy equations. So before, we had single particles for our MATLAB projects where we could just implement the equations as is. and that's the U and T equation here. But now we're actually dealing with an infinite number of particles, so we can't use this. We have to sum all of the particles' energy, the potential and kinetic energy, for all of the particles. So we have to complete that integral by hand and then include those equations in the history array here. Next, we can go ahead and look at what other information we have to store. So we have to think about what do we need to remember about our pendulum. Well, let's just look at the geometry. So we have the pendulum rotated and it's up the inclined plane. So we're going to want to get from the origin to the roller, and then from the roller out to out to the end of the pendulum, basically. So we're going to want to be able to store all of that information. So where the roller is and where the tip of the pendulum is. So next we update T. And then here's where we're going to actually need Newton's method. We're going to have to calculate a new acceleration, but the acceleration is dependent on something, so we have to implement Newton's method. So you can go ahead and look at the course notes for full derivations on how to do Newton's method. But let's just look at this left note section. So if the equation of motion depends on velocity, you're going to have to use these numerical analysis parameters inside of Newton's method. If the equation of motion depends on position, you're going to want to use the numerical analysis parameters shown in blue. And if we just look at the drag problem example, if we look at the equation of motion, the residual equation, we have that the equation of motion depends on velocity. So inside of our Newton loop, we're going to want to update velocity after each iteration. So now we execute trapezoidal rule, and that can stay exactly the same as usual. And then you can also get rid of any of the impact problem detection information in your code. And then we're going to update AOLD, VOLD, and XOLD for the for the next iteration of our time-stepping algorithm. And that's it for this video. One thing you also want to remember is that while you're debugging your code, you want to make sure that your history array matches what the history array of the movie code has, because the movie code can help you debug your code in the future, and that's going to help you get a sense of what's the pendulum doing, how is it moving. All right, that's it. Thank you so much.